Good morning, ladies and gentlemen. Can you hear me at the back? Great, thank you. Pleasure to be here. Thank you very much for inviting me. I've learned a lot from this meeting. I'm going to be talking about structure and dynamics from random observations. Now, in terms of structure, I will really show you structure of real objects, at least in biology, and the dynamics also examples from physics. However, I really would like you, when you see structure, think of similarity-based reconstructions, and you think of dynamics, think of time series or things which are data which are ordered. I'd like to acknowledge my collaborators, particularly the group in red from UWM, but also other institutions. I'll show this again later. So in physics and in science in general, the concept is that the best experiments are the one which exercise the greatest level of control. This actually limits the amount of information you extract. If you make an object eat, then you can only watch her eat, do nothing else. The data-driven approach, however, says that the richest data sets really come from random observations. Google discovered this a long time ago, so nothing new here. And once you have your data, of course, you have search algorithms to extract specific kind of information at will, ideally without any preconceived notions, templates, or priors. And of course, the tools, there are many, but the tool which I'll be talking about here is manifold learning, which means gleaning information from the geometric structure of the data, plus constraints due to the nature of the relevant spaces in which the data were collected. Now, I'd like to show you three examples, if I have time. The first one, which is popular with mathematicians, is taking random snapshots of an object in an unknown orientation, and then recovering the 3D structure of the object. Examples are viruses, ribosome, single proteins. Much more interesting is when you want to see an object, a machine of some kind, perform a useful function. Particularly, the examples I'll show here are nanomachines at work, where instead of having snapshots just from unknown orientations, they also emanate from unknown states of the machine undergoing some kind of operation. And I'll show you molecular movies along the work cycles of these nanomachines, how you can map energy landscapes and determine nanomachine thermodynamics. And of course, these concepts can be easily extended to astronomy or even the market. Finally, I'll talk about dynamics, and that is just by that I mean extracting accurate dynamics from highly inaccurate data. That's to say, data which are not only corrupted by noise, by pixel noise, but which are strongly corrupted in the sense that timestamps associated with them are highly inaccurate. Okay, now I have to give you a warning, and that is that when it comes to many kinds of algorithms, then 99% work with toy models, because the toy models were invented to work with a technique. This number drops to about 90% if you use simulated data. If you add noise to simulated data, about 9%. And in our experience with experimental, it is about 0.9%. These are the laws of the nines. And in order to make sure that I don't fall into that trap, I will not show you any simulated data unless it's accompanied by experimental data at the same time. So all the results I'm going to be showing you will be from experimental data. Now, here's an experimental snapshot obtained by so-called cryogenic electron microscopy. It doesn't really matter. And it's a snapshot of a calcium channel of the kind which is responsible for heart attacks in your heart muscle, and just the still snapshots. Now, we take a collection of these snapshots, several 100,000, and I'd like to show you, this is in fact the image you can reconstruct from snapshots of this kind. The resolution is about 3 to 4 angstroms, and I'd like to show you actually a movie extracted from data of this kind, no timing information. The calcium channel just in equilibrium, and we can talk about that later, where you can actually, I'll show you later, you can determine the work cycle of this nanomachine in action. This was obtained by manifold learning from experimental data, as I just described. Now, what do I mean by manifold learning? Of course, we're talking about some kind of vector data. For example, give a snapshot. vector data here, and you can represent the vector, a bunch of these snapshots as a bunch of vectors, or if you like, a cloud of points in some high-dimensional space. In this high-dimensional space, which we are always dealing with highly noisy data, you can ask yourself the question, what's the difference between noise and data, and noise and signal? And the answer, of course, signal is somehow correlated. And so the information content of the data set is reflected in some kind of a hypersurface, essentially a manifold, actually usually a Riemannian manifold, which you can extract from the cloud of points. Now, the dimensionality of this manifold directly tells you about the number of intrinsic degrees of freedom exercised by the system during observation. So you can already glean a good deal of information from that. However, ideally what you want to do is to extract the information content and understand the information content represented by this manifold. And if these snapshots represent the positions of somebody's head, the snapshots of somebody's head from different orientations, then of course this manifold will be ultimately intrinsically three-dimensional, and you actually have a three-dimensional model of somebody's head if starting from one point, which is the image of somebody's face, for example, viewed from the front, and you can purposefully navigate to any other point on this manifold, for example, what the image looks like, what this person looks like from the back of the head. That is to say, extracting and understanding the information content of the manifold is tantamount to purposeful navigation on this manifold. So let's follow this example of somebody's head again. You observe this head from different orientations. So you're looking at a latent space of orientations in this group, in this case, the group SO3 group. And there's some kind of a nonlinear embedding taking snapshots, which produces a kind of a manifold, which topologically, of course, is still SO3, but highly distorted. The difficulty here is all you have, of course, is this manifold. You don't know the nonlinear embedding, which related one to the other. And the fact that the metric, which you may know in the space of orientations, is well known, and the fact you may now determine the metric in this manifold, as we heard yesterday from the beautiful talk. Nevertheless, you don't know the relationship between the two metrics in the two spaces. Now, that's important because what you have, of course, is a manifold. You want to purposefully navigate on this manifold. For example, you want to see my head rotate about a single axis, but I don't know how I can do this in this space, and that makes it actually very difficult to interpret the information in the manifold. Now, the technique which I'm going to be using for the rest of today is a diffusion map technique, and diffusion map has this nice property that when you do the manifold embedding, this dimensionality reduction, then the manifold is represented in terms of eigenfunctions of a well-known operator, the Laplace spectrometry operator. The difficulty, as I mentioned earlier, is that the manifold has inherited what is known as an induced metric. It's essentially an unknown metric, and so you cannot purposefully navigate, and therefore it's difficult to extract information content. The only thing I want to say, but in the way of bypassing, is that there is a powerful group of you have powerful information from the nature of space in which these operations are performed. For example, if you know that the snapshots are from somebody's head, then you know that in the latent space you're dealing with has a particular peculiar symmetry, actually is the group of the SO3 group with an appropriately known metric. It turns out that for nearly all scattering experiments, and when the data stem from any kind of scattering experiment, and you can write the metric of the manifold in terms of a sum between a well-known metric, which is independent of the type of object you're looking at, plus a residual, which is an object-specific term. This immediately allows you to recover the orientation of the object, because now the eigenfunctions are known, specifically in this case of the Wigner-D functions. That's not an important point, except that the fact that you know the metric means that you can extract the orientation. And here's and I want to show you how well this works. This is really a solved problem, but just to buy you an example, if you use a simulated snapshots of cryo-EM, again, of a chaperone molecule, this is the experimental snapshot obtained at a dose of 20 electrons per angstrom squared. This, for us, is a high signal, and so we've pre-processed the image to reduce the dose by another factor of 12, and these are the recovered three-dimensional object structures at zero noise, experimental level noise, and experimental noise increased by a factor of 12. Solve problem. Really what you're interested in is you want to see how an object actually performs what it generally performs. So in the biological sense, for example, you want to understand not just what the structure of some molecule is or some nanomachine, but how it performs its function. Now, of course, it is function which determines structure, and function involves continuous changes in structure. Now, these continuous changes in structure are called conformations, but I want to suggest to you that, in fact, life does rarely clusters. That is to say, although we take large graphs and we cluster them, that doesn't necessarily mean that the cluster structure is intrinsic to the data. In fact, in the great majority of cases, the intrinsic structure is really continuous. Nevertheless, I want to go back to the biological systems where you look at changes in structure in the course of performing some function. And these changes in structure, of course, involve changes in energy. Otherwise, there would be no specific structure. That's to say, whenever you want to look at some machine in operation, in the most general sense, then you need to look at its structure, underlying intrinsic structure, and you need to associate that with the energy. That's to say, you want to make molecular movies along energy landscapes, and I'll say more about that in a moment. Now, the difficulty about mapping, for example, conformations is that, of course, you're viewing this biological machine from a random unknown orientation in a random point in its function. And the difficulty is the metric of the manifold which you get, of course, has diagonal elements which depend only on the orientation and only on the conformation, but they also have off-diagonal elements where the two are coupled together, and it is extremely difficult to decouple this. Actually, it turns out that in the extreme cases where the change is due to orientation, factor 1, are large or much larger or much smaller than changes due to factor 2, in this case conformation, you can solve the problem because by an iterative way, which I'll be happy to describe to you in private. Now, the final point about this is that, of course, whenever you take a snapshot of an object, it could be somebody writing email or it could be a biological system in function, the difficulty is you're bombarded by noise, by random events. Somebody is giving his spouse a hard time, but if you're a molecule, you may be being bombarded by Brownian motion of the particles in the bath. That's to say, any single trajectory of a single machine is unique and irreproducible, and therefore essentially devoid of much information. And only ensemble averages are meaningful. In order to find out whether somebody likes chocolate, you don't just look at a random appearance of the word chocolate in her email, but you have to see that repeated. In the same sense, if you want to look at how a biological machine performs what function, you have to look at many trajectories and form an ensemble average. That's to say, the thermodynamics is important, and it's really the nature of the ensemble use of averaging is key. You can't average over all the states of the machine because the data is heterogeneous. And so you first have to classify the data, which generally is called clustering. Actually, in this case, you have to deal with continuous changes, and then you have to form ensemble averages over homogeneous ensembles. But of course, as I said earlier, complete description requires an ensemble average over an energy landscape. Now, what do I mean by that? And this question really came up a little bit a couple of days ago when I asked stupidly, I must admit, for reaction coordinates. The point is that if let's take a very simple case, for example, a biological system, then any kind of function which the biological system performs involves thousands, if not millions of atoms moving in concert. And of course, there can be different types of concerted action. You can think of a knob you turn which moves the entire collection of millions of atoms in a concerted way. That knob I call a reaction coordinate, and of course there can be several reaction coordinates. I can talk and I can eat. And they involve concerted actions. Now, a question came up, why do the reaction coordinates have to be orthogonal or independent? The problem is this. If you define a reaction coordinate by looking at my jaw, then you cannot distinguish whether I'm talking or eating. It is only when you identify mutually independent reaction coordinates that you have a complete and appropriate description of the system. If not independent, the reaction coordinates must be at least orthogonal. That is absolutely critical. And so finally, let's take a very simple system where there are two reaction coordinates. And then on the third axis, you see the energy associated with any point on this landscape. So you have an energy landscape. At each point, you have specified the value of two orthogonal reaction coordinates and the energy associated with that. Now, function corresponds to a path traversed on this energy landscape. And if you have a machine, then this path will be closed in order to have a repetitive function. Now, here is the energy landscape of the yeast ribosome. The yeast is a machine which reads the genetic code, one codon at a time, and taps out a protein. This is the experimentally determined energy landscape of the yeast ribosome by manifold learning, and you can see the closed path, which is associated with so-called translation, reading the genetic code and tapping out a protein. Now, of course, the way we got these snapshots, this energy landscape was from the kind of raw, lousy snapshots I showed you before, and this is the three-dimensional structure, conformational changes associated with the work cycle of the ribosome. Now, you might see a dot flying around this work cycle, and so this is essentially a molecular movie of the ribosome over traversing its work cycle. Now, in order to show you that this is not a one-off, here is a molecular movie along the energy landscape of the calcium channel in heart muscle, obtained from similar machines. And for those of you who are biologists here, you're actually seeing the alpha helices slip over each other. And if you look at this in greater detail, you can actually see salt bonds forming and rupturing as these alpha helices slide over each other. So far, I've talked about movies which are and energy landscapes which are derived by looking at a number of random snapshots based on similarity. I had no timing information before. Now I'd like to talk about dynamics where you have timing information. Now the difficulty, now if you like going to summarize, the energy landscape which I showed you before reveals the degrees of freedom and allows you to identify useful, meaningful reaction coordinates. Dynamics, however, shows how a functional path is traversed. Let me be very specific. If I have a similarity-based movie, I cannot decide between 2 steps forward, 1 back, 2 steps forward, 1 back. Whereas if I have timing information, I can do that. And so if you want to know how, in what order the energy, in what particular sequence of events, for example, a particular energy value was circumvented, they need additional timing information. Now the difficulty is that dynamical information is often limited by noise and timing uncertainty. This is very important. We heard a beautiful talk yesterday about transaction-based data which allow you to recover economic cycles or perhaps predict economic cycles. Now, the time that a transaction was conducted is only a rough indicator of when the person had the money to make the purchase. Now, let's just say even when you have extremely precise time labels for a transaction, it doesn't necessarily give you accurate information about the causal effect. And so the timing uncertainty is really ubiquitous, not only in physics, but also when people think they have exquisite timing information. So the trick here is to get accurate dynamics despite extreme noise and timing uncertainty. And I want to convince you over the next few minutes that you can get timing uncertainty about a factor of 300 better than your timing accuracy allows. But in order to, let me show you the kind of data we're using. This is experimental data. Each vertical line here is a spectrum. It does time of flight spectrum of something exploding. It doesn't really matter. And so here you can see essentially a spectral movie. This is the delay time. Goes from about minus 2.5 picoseconds to plus 2.5 picoseconds. And if you zoom that in, you can see that you get no more information here. You're really in the pixel domain, the vertical axis, you're limited by Poisson noise, and in the horizontal axis, you're limited by timing uncertainty. And in fact, the timing uncertainty is about 280, about 300 femtoseconds. Now, by a technique which I will describe in a moment, I'd like to show you, if you take this movie, experimental movie, and put it into the technique I'm going to describe, this is the outcome. This is the dynamics you can extract from that data set. And it turns out that the timing resolution is now about 1 femtosecond. Now, it's generally been a tenet of basic physics that if your timing resolution is X, then there's no more information beyond the timing resolution. This allows you, and electronics, where people don't know about physics, they've worked hard, and they've improved the timing uncertainty by a factor of 10, by about 10 to 20%. We're talking here about a factor of improvement of a factor of 300. Now, for those of you who are physicists, you might appreciate this. This is an experiment where you take a nitrogen molecule, you hit it very hard, and you look at it explode. And of course, when you hit something like a bell very hard, it rings, and this provides a wave packet. And these are the particular frequencies of the wave packet. Now, we actually did this work, and then subsequently to our work, the frequencies of these oscillations were calculated. And I'd like to show you between what we measured in the presence of 300 femtoseconds of timing inaccuracy. This is the measured period, and this is what is theoretically calculated afterwards. And it turns out that we are able to see 1 femtosecond timing data in the presence of about 300 times more timing uncertainty. Now, how does that work? Well, the issue is really, the concept is really very simple. If you take a pack of cards, perfectly ordered, you do a perfect shuffle, then there is still some remnant of the original order there, albeit very weakly. And that's to say you have a weak arrow of time, and then as soon as you understand there is a weak arrow of time, of course you can use well-known techniques to extract that weak arrow of time, and that's exactly what we've done. Now, the technique we use, of course, is to recognize that you can use SVD to extract the signal. However, we perform the SVD on a curved hyperplane. The point is that the intrinsic structure of the data is not linear, and so normal SVD is an inefficient way of dealing with that, and so we essentially perform SVD on the curved manifold. But before doing that, I'd like to give you one more refresher on things which you're sure to know, which comes from a beautiful theorem proved by Tarkins. The important point is that in order to see this weak arrow of time, we don't look at the individual snapshots, but we look at a sequence of snapshots and then move this sequence one click at a time. And so specifically, we look at time series data with time-lagged embedding. And so we're looking at a series of snapshots, x of t minus delta t, etc., and we concatenate a superframe consisting of c individual frames. And then we do the analysis on these superframes. Now, it turns out this beautiful theorem by Tarkins says that if you actually provide a time-lagged embedding, then you recover all the degrees of freedom of the system, even though in projection you didn't measure them. It's a very powerful technique. I'd be happy to describe that to you in more detail privately. Now, I'm going to do straight SVD on the manifold. Nonlinear SVD, if you like, that's a misnomer. The only difference here is that I'm going to be calling the left and right singular values singular vectors as topos, topograms, and chronos for chronograms. Now, the important point about this is that you have some kind of a nonlinear manifold, and when you do manifold embedding, it gives you a Euclidean description of this manifold. That's to say, you essentially, if you like, unfurl the manifold, and because now you have a Euclidean description of this nonlinear manifold, you can do SVD. Specifically, what you do is that you take your data matrix and you project it onto the manifold in a nonlinear fashion, hence the Riemannian measure. Then you perform SVD on this matrix, and then you project back into the time domain that you were originally interested in. Now, this work is being described in detail, and I'd be happy to describe it to you and discuss it with you in private. But this was not universally appreciated by all the referees in Nature, and one of them said that if you really think you could do what you could do, then take your output signal, the dynamics you've recovered, put in the pixel noise, that's Poisson noise, put in 300 femtoseconds of 300x timing uncertainty, and then do it again. See if you get back what you got. And in fact, one of these is the input signal. The other one is the signal we recovered from it using our technique. And I'd like to ask you to tell me which is which. And if you can't, then this might help, because this is the difference in the input and the output, and the mean deviation between them is 0.2%. And so not only do we have extreme accuracy in determining timing to a factor of 300 better than the uncertainty, but we can actually recover the original signal to an accuracy, a mean accuracy of around 0.2%. So let me conclude. Random observations contain a wealth of information. However, they have ultra-low signal-to-noise ratio in many cases, although we may not be aware of that, and they often come from unknown states of the system we're interested in. And they have uncertain timing. Now, these are implicit in the data we get, even though they may not be explicit, in the sense that many dynamical data have intrinsic timing uncertainty. We're not aware of them. And many types of information have intrinsic noise, whether they're emails or snapshots of the ribosome. Now, geometric machine learning is a key to unlocking this information with a few relatively simple tricks and general constraints, really high-level general constraints. For example, constraints about the nature of space in which the observations were made or certain operations were performed allow you to not only to extract the information, but also understand it. New in this also, relatively new, is access to what I would call super resolution dynamics. That's to say that getting extremely accurate dynamical information and realizing that precise timestamps or precise ordering of the data is not the same as accurate timestamps or accurate ordering of the data. And this, of course, is applicable to all vector data. Thank you very much.